Good day everyone, and welcome to the second lecture in the optimization module. Now today we're going to have a look at genetic algorithms, which of course is a specialization of evolutionary algorithms which we covered previously. Now when somebody refers to an implementation of an evolutionary algorithm, they most probably refer to a genetic algorithm. It's one of the first easy implementations. It's pretty straightforward to implement, and it's actually pretty powerful. It was popularized by J.H. Holland, which was, of course, is regarded as the father of GAs. Now, it follows the general EA algorithm or paradigm quite closely with the following specific details. First of all, a bit string representation is used for the candidate solutions, although I would argue that an array of integers or array of bytes or floats is equally valid, because a float or integers, it's just an abstraction of a bit string anyway. So I would argue that that definitely also qualifies. But the standard vanilla genetic algorithm used the standard bit string. For selection, we have proportional selection. So remember, that is where the fitness of the individual plays a pivotal role in whether it gets selected or not. And this is used for selecting both the parents for recombination as well as the next generation. And then, of course, you have one-point crossover is used as the primary reproduction operator, and then bit flip mutation as a background operator with less importance. Although you'll see that mutation is actually a pretty important step to get good solutions. There's also a number of variations on this. So this would include things like mass extinction, culling, population islands, even interactive fitness functions. But we'll have a look at each of these in the next few slides. Okay, so crossover can be divided into three main categories. The first is asexual. Now with asexual reproduction or crossover, offspring is generated from a single parent. Now this is kind of a form of cloning, and later on we'll get to why this is actually different than just mutation. But that's where you only have a single parent that takes part in the reproduction. Then you've got sexual reproduction, where two parents produce one or two offspring. And then lastly, multi-recombination, where you have multiple parents that's used to create one or more offspring. Multi-recombination tends to have a high take over time. It decreases the diversity. That's why sexual reproduction is quite commonly favored in most implementations. So during the selection of the parents, remember you need parents in order to create offspring, the following must be considered. So avoid selecting the same individual, because then you just basically reduce sexual reproduction or multi-recombination to asexual or to sexual reproduction. You decrease the number of parents, and of course that's not what you want. So the parents need to be different. And then due to probabilistic selection, again the same individual can participate in multiple recombinations. So, and of course that's not a bad thing per se, because you want a higher probability for the fitter individual to proliferate its genes across the population. So that's not necessarily bad, but it's good to take, to note that, because it will result in faster takeover time. And then of course, once you've got offspring and you've got parents, you need to find a way to which ones are going to survive. So there's various replacement strategies. You can replace the worst parent, you can replace the worst individual in the population, you can replace all the parents with all the offspring. There's numerous ways, and we're going to have a look at each of them. So when you get to a sexual reproduction or crossover, most implementation applies what's known as a mask. Now this mask it's more an abstraction than really a mask, but it's useful during the explanation phases and to get an idea of how it works. But once you implement it in code, you typically skip the creation of the mask. You just copy from the parents directly into the offspring. But once we get to the implementation phase, I'll show exactly what I mean by that. So you'll typically start with your two parents. So here we've got X1T and X2T for a specific generation T. And then you produce offspring X1 tilde T and X2 tilde T from these two parents. Or you could only create one child, one offspring, X1T, but typically two children are created to enforce the whole idea of symmetry between the parents, because you don't necessarily copy the same amount from each parent. But if you swap them around, then of course you get symmetry back. Now the mask decides which genetic material is copied from which parent to which child, and we'll see that in a moment. And then the binary approach can be applied to both the integer and the floating point representations as well. But now instead of just using a single bit at a time, you copy a whole integer or a whole float at a time. But you'll see how that works in a moment. So for 1-point crossover, you first of course, need to have your parent. So there's parent 1 and there's parent 2. And then you create your mask. And here's your mask. So the mask is created by selecting a random point. So for example, over here. And then everything to the left of it, you make zeros. And everything to the right of that, you make ones. And then you use the mask to copy from the correct parent, or from each parent into the offspring, as the mask indicates. So for example, you'll see that there's zeros to the left, so that comes from parent 1 in offspring 1. Here's offspring 1. And of course the last part, where it's all ones, that comes from parent 2. Then of course you do exactly the same for offspring 2, but now you swap it around. So the zeros comes from parent 2 and the ones comes from parent 1. And in this way you get 2 offspring from 2 parents and an equal sharing between genetic material, even though the individual offsprings are not symmetrical, but combined they are of course symmetrical. So this is 1-point crossover. And of course, if I leave you with 2-point crossover, I'm sure you can figure it out. So again, you've got parent 1 and you've got parent 2, a blue parent and a green parent, but now with the mask you select 2 points. So let's say over there and over there. It can be any point. It doesn't have to be there. Remember, these points are selected randomly. That goes for 1-point crossover as well. And then exactly the same as with 1 point. So where you've got 1, you select that from parent 2 for the first offspring. Where it's 0, you select from parent 1. From parent 1. And this, so it's these sections comes from parent 2 in this case. And the blue section you see comes from parent 1. And then of course you replace this, or you repeat this process for offspring 2, but you just swap the values of zeros and ones together. You swap the mask, so that you've got an inverse of the previous operation. And that's 2-point crossover. And I'm sure you can extend this to 3-point and 4-point crossover if you really have to. But typically in practice, 1 and 2-point crossover is the most commonly used. Then the last kind of crossover is uniform crossover. Now with uniform crossover, you create a random mask. So the mask consists of ones and zeros in any order. So there's no crossover point or anything like that. You literally create a mask with random ones and zeros. And then exactly like with 1-point and 2-point, you use the number to indicate from which parent you copy to the child. So for offspring 1, okay, so the moment you've got a 1 over here, that would come from parent 2. So the first bit location in offspring 1 is a green from parent 2, and then the next one is a 0, so that comes from blue parent, the second position in blue. And in that way you copy the positions, or you copy the material in the parent over into the child. And of course you do the same for offspring 2, but now you flip the bits. Now uniform crossover is a very powerful crossover technique, and it works really well, but only really in scenarios where the relative positions of the genes doesn't matter. So for example, let's say you are solving the knapsack problem, where you have to select things that are placed in a bag. The position of the items inside this array, which items you select and which items you put in other words, the order in which you put them in the bag, it doesn't matter at all. So for that kind of approach, uniform is perfect. But let's say you've got a problem like the traveling salesman problem, where you need to order and visit cities in a specific order. Now uniform crossover is not necessarily as good, because you are more interested in sections of genes that represent something. So the order and the relative positions relative to one another starts to become important. And for those kinds of problems, 1 and 2-point crossover is better. Of course, with the traveling salesman problem, there are some caveats that you need to be aware of, but just be cognizant of that. If the relative positions are important, 1 and 2-point crossover works well, and if it doesn't, uniform is almost the go-to approach. Okay, so that's crossover when you've got 2 parents. So what about multi-parent crossover? Now there are numerous ways to implement this, and one technique proposed by Bremerman simply goes like this. It generates a single offspring by setting the gene in the location of the offspring to the statistically dominant gene in all the parents that are participating in the crossover. So let's say you are creating this child, Xij tilde. I is just an ID for the child, and J refers to the index in the array or the bit string that you want to set. Then you've got 2 values here. You've got this in mu prime. So in mu, that's the number of parents that's participating in the crossover. And you've got in mu prime, that's the number of parents with a 0 in position j in its array. So essentially what this means is that if most of the parents, okay, more than half of the parents have a 0 in that location, so it's the dominant gene, then that location is also going to be a 0 in the child. And if it's even, it's also going to be a 0. Okay. Of course, you can also say that if it's the same, so it's an even number of parents, and it's exactly half, then you can perhaps set it to a random 0 or 1. That's also fine. Otherwise, if the value 1 is dominant in that location, you set that location in the child or the offspring also to 1. Now, multi-parent crossover tends to decrease your diversity quite quickly over time, so your population is uniform. Not necessarily a bad thing, especially near the end of the algorithm, when you want the algorithm to start to converge. Then of course you can apply this. So when you apply crossover to a floating point representation, I mean, you open yourself up to quite a few alternative, approaches. So it's possible to use a binary representation for the floating point numbers, and then you can use 1 point and 2 point crossover, like you just use, or uniform. That's perfectly fine. Or if you have an array of floats, I mean, you can apply that to the entire float value. So with 1 point, you copy the first half of the array as is, and then the second part of the array from the next parent. That's also fine. But because we are using floating point numbers, you can use all kinds of blending approaches, where you would take the gene from the one parent and that from the other parent, and then combine them in some way to form a whole totally new number. And we're going to have a look at that next. So it's Wright's linear operator approach, his directional heuristic crossover, which is very interesting, and then Mikhailovich's arithmetic crossover. And this is specifically tailored around floating point representations. Okay, so let's quickly have a look at Wright's approaches. So his first approach is the linear operator approach. Now, given two parents, x1t and x2t, you'll see that they're in bold because we're working with full vectors. Three candidate offspring is generated as follows. First of all, one that we simply just add the two vectors together, x1 plus x2. Next one is 1.5 times x1 minus a half x2. And then lastly, we just swap them around. So minus a half x1 plus 1.5 x2. Okay, and then from these three offspring, you select the two best ones. And of course, that's the blended approach. But there's two very important things that you have to keep in mind. The first is that your values of your genes need to be centered around the origin. So in other words, something like from -2 to +2. Otherwise, this x1 plus x2 is going to be biased towards positive values, depending on where your center is. So it needs to be centered around the origin. And of course, you also need to be careful because sometimes a gene can go out of bounds. So let's say you've got a range from -1 to 1, and the parents have both a 0.9 at a position. If you add them together, that's going to give you 1.8. So that's out of bounds. So you have to cap it then at 1. That's not necessarily a bad thing, because you can argue that if the parents have a high value at a gene's location, it makes sense to increase it in the child. And of course, if that turns out to be a bad idea, natural selection will automatically bring that value down. That's the beauty of evolutionary algorithms. Then, of course, there's another approach called is directional heuristic crossover. And this works as follows. Again, we've got two parents, x1t and x2t, but now there's a very, very important requirement. So basically, x2 needs to be fitter, or at least equal in fitness to x1t. That's very important. And then we create a single offspring as follows. You take the best parent and you subtract the worst parent from that. Okay, for each component. Okay, and then you scale that by some random value between 0 and 1. Okay, and then you add that value to x2. Now, what does this do? The idea with this is that it doesn't simply just mix genes, but it looks towards the direction of improvement. So it tries to force the best individual to become even better, so that the movement is in the direction of the beta parent. So it uses the fact that a vector is pointing towards improvement. So, but of course, the best way to illustrate that is by means of a graphic. So let me quickly show you. Okay, so let's say you've got the following two parents. Here's x1 over here, and here's x2. And of course, x2 has a better fitness than x1. Okay, that's very, very important. So of course, the first thing you need to calculate is the difference between x2 and x1. So x2 minus x1. So to easily do that, we just negate x1. So minus x1 is over here. So the minus 3 becomes a positive 3, and the 3 becomes a negative 3 for the y-axis. And now we've got a negative x1 over here. And now we simply add this to x2. So x2 plus x minus x1 gives us this value over here, this v, 8 minus, or 8 and minus 1. So 5 plus 3 is 8. 2 plus minus 3 is negative 1. And now, of course, this we scale. So let's say we scale that by 0.5. And now it gives you this uv. So u is the scaling factor of 0.5. So that the 8 becomes a 4. And the minus 1 becomes negative a half. Okay. Now we've got this value. And now this is what you're going to be added to x2 to get the new parent. Or not the new parent, the offspring. So 5 plus 4 gives us 9. 2 plus minus 5 minus 0.5 gives us 1.5. And this is the new parent. Okay, so if you look at this, what basically happens is x1 that points over here has a weaker fitness, and x2 points over here. So the idea is that the child of x2 should move in the opposite direction that x1 is pointing. That's the whole idea of this heuristic crossover. So it tries to move away. So if I actually move this x1, you'll now see how that affects the offspring of x2. And I can actually do this interactively. So if I move this, see where the star moves away, which is this child, totally away from where x1 is pointing because it's not good. So if I move it downwards, the star goes up. And if I move it all the way to this direction over here, you see, so now x1 is pointing further than x2 over here. And of course, that means that the star, which is the offspring, should go in the opposite direction. So that's the whole idea, is that you use the fact that x1 is weaker than x2 to try and determine where, in which direction should we actually move the offspring. So the actual fitnesses of the individuals are then used to guide the direction of where the offspring should be. And that's Wright's heuristic crossover. Now, Michalowicz's arithmetic crossover is used for multi-parent recombination for floating point values. So you create one offspring, and what you do is beforehand is you create a number of factors or multiplication factors. So for example, in this case, we've got gamma L for the n mu, the number of parents. And of course, you want this whole sum to add up to 1. So for example, you can choose 0.1, 0.2, 0.4, 0.3 for 4 parents, and all of them add up to 1. So 0.3, 0.4, 0.7, 0.9, that's 1. And then the child offspring is simply calculated as the weighted average of all of these. So for example, xij tilde, that's our offspring, is simply take every component j of all the parents, multiply each one with its corresponding, let's say, recombination factor, and you add that up, and that gives you your child. So for example, for the first parent, you'll multiply everything with 0.1, 0.1, 0.1, 0.1, and for the second parent, you'll multiply its components with 0.2, the third with 0.4, and the fourth with 0.3. And that's essentially this blended approach, Michalowicz's arithmetic crossover. Now, Michalowicz also proposed a two-parent geometrical crossover. And how this works is you take the components of the two parents, x1j, x2j, and you multiply with one another, and then you take the square root. But of course, now you have to make sure that this product is always positive. So typically what happens here is x1j is positive and x2j is also positive, just to make it easier. And you have to have a special case for 0, because if one of these components is 0, this product is going to be 0, and that might not be exactly what you want for crossover. But anyway, that's how that works. And of course, you can also generalize this for multi-parent. So instead of taking the square root, you raise every component to a power from alpha 1 to alpha n mu, which is of course the number of parents that you have. And then you just have to make sure that all these exponents it has to add up to 1. And then of course, in this way, you can have a multi-parent crossover. Debon and Gravel also proposed a simulated binary crossover. So here we start with x1t and x2t. These are the parents. And with this, you're going to create 2 offspring, x1 tilde and x2 tilde. Now, how is that calculated? First of all, we have this constant inside, 1 plus gamma j and 1 minus gamma j. We'll get to that. But that's 2 components that we multiply with each of the components inside the parent. So we take 1 plus gamma j and we multiply that with x1j. And 1 minus gamma j, we multiply that with x2j. So in that way, we combine the 2 parents to form the offspring. And then once this is added, we multiply that by 0.5 or we divide it. And we do this for each and every component. And then for the second child, exactly the same. The only difference now is that you swap these two components around. So where you had 1 minus gamma j that you multiplied with x2, now you multiply that with x1. And in that way, you can get 2 offsprings from your 2 parents. Okay, so where does this gamma j come from? Okay, this is this part over here at the bottom. Now, the first part is, let's chat about rj. Rj is a random value that's uniformly generated between 0 and 1. And eta is known as a distribution index, which is typically 1. But you can experiment with other values as well. So if you look at this power that we have in both equations, it's 1 plus eta plus 1. So in both, if it's 1, it's going to just be the square root of this value. So the square root of that and the square root of that, that's the vanilla approach, when your eta value, your distribution index, is equal to 1. So if your random value is smaller than 0.5, your gamma j value is simply 2 times whatever that value is. Okay, so it's slightly increased. And then otherwise, if it's greater than 0.5, it's a large value, you take 1, you subtract whatever that value is from it. So this would be a value, in other words, smaller than 0.5. And then you multiply that value by 2, and it's 1 over that value. Now, the best way to see this is if we look at a graph. So let's quickly have a look at that. Okay, so here's our graph. And then on the x-axis, we've got our rj value. Just put that there. And on the y-axis, we've got gamma j. Okay, so there's gamma j. Okay, and the idea is that if rj, our random value, if that is smaller than 0.5, then this represents the blue part of the graph, which is of course this first equation. So this first equation is blue. Okay, and if rj is of course greater or equal to 0.5, then we use this equation, and this corresponds to this red part that you see over here. And then of course the yellow and the green. The yellow is 1 plus gamma j, and the green is 1 minus gamma j. So when your rj value, this random value, when it's very close to 0, you'll see that the 2 values are almost identical, which means that this is almost like the 1-point crossover, where the point you chose is exactly in the middle. You're going to equally contribute, each parent is equally going to contribute to each of the 2 offspring. However, when rj gets close to 1, that's the opposite. Then of course your yellow and your green is quite far away from one another. That corresponds to that 1 point being either right in the beginning or right at the end. And you only take a very small part of the one parent and most of the other parent to actually contribute to the offspring. So in this way, you basically simulate the 1-point crossover, but with floating point, and of course merging them together in this fashion. And that's crossover, which brings us of course to mutation. Now the aim of mutation is to introduce new genetic material to an existing individual. It's used in support of crossover to ensure that the full range of alleles is accessible, because it might happen that during the initialization phase that a specific gene does not have a specific value. So you can do crossover as much as you like. You will never be able to evolve that correct value for that gene. So mutation is also applied at a very low probability, typically something like 2% or less, in order to so that you don't distort your individuals too much. Now, there's a number of binary mutation strategies that have been developed. First of all, you have a uniform mutation where the bit position is randomly selected and negated, so it's flipped. You have what's known as an in-order mutation, where 2 mutation points are selected and only bit position within those 2 points have the probability of being mutated. And then, of course, Gaussian mutation. Now, with Gaussian mutation, this is for floating point and perhaps to some extent integer values. So you don't mutate a single bit, but you mutate a complete value. Then, of course, you can use Gaussian which is added. So there's a higher probability of adding or subtracting a small value than it is to subtract or add a larger value. Okay, so basically it works like this. So with random mutation, you simply pick your bits. So let's say we're going to pick this one, and this one over here. And you'll see that after mutation, that green became a blue, the blue became a green, and this blue one became a green over here. For in-order mutation, basically you'll select points. There's P1, for example. That's the first point. There's point 2, P2. And you only mutate bit positions inside these 2 points. So basically, random mutation is almost like in order, but you take the full range. All bits has the possibility of being mutated. Okay, and that's essentially mutation. Now, with floating point representations, going to binary and then going back to floating point sometimes is not that optimal. So one of the first mutation operators that was proposed for floating point is called the uniform mutation. So essentially it works like this. So Xij prime is the individual after mutation has been applied, and then you're going to pick a random digit. Either you're going to choose 0 or either you're going to choose 1. And remember, these Xij values are all floating points. It's not, or floating point values, it's not binary. So basically, you're either going to add something to that value or you're going to subtract something to that value, all depending on whether this random bit is 0 or 1. So what do you add? Essentially, you add a random value. Okay, this is this delta, which is the difference between the maximum allowed value minus the current value. So if the bit is 0, you're going to increase Xij up to the maximum that it can be. That's all that this means. So it means if you're close to the maximum, then you can't modify it that much, but you can only go slightly higher. And of course, the opposite is true. If it's the random value is 1, then you're going to go down, and you can only go down up to the X min value. So this random value that you see over here, these 2 delta values, is just a way to make sure you cap it so that it doesn't exceed the allowed value. So you either increase it or you decrease it based on some random bit. Which brings us to the macromutation operator known as headless chicken. Now, this was proposed by Jones, and basically what this means, you create an offspring by combining a randomly generated individual with the parent using the normal crossover operator for that algorithm. So this is not really a true crossover because there's no inheritance taking place. It's a kind of a mutation, but the point is you're creating a new individual. And if you create a new individual, that's not just pure mutation, it's more a kind of asexual kind of reproduction. So the idea with the headless chicken is once you find out that your algorithm might be stuck at a certain location, so it's at a local optima, you can perhaps switch on the headless chicken just to add some variety to your population, and then once it's out of that rut, you can switch out of headless chicken to see if you can find a better solution. But the headless chicken definitely is going to add a lot of chaos and a lot of diversity to your population. So I won't use this as is in the entire algorithm, but it's an interesting algorithm to switch to if you need some diversity in your population. So when it comes to your control parameters, the GA's performance is influenced by the mutation rate PM and the crossover rate BC. You usually have a very high rate for your crossover because you want most of your individuals to be created from genetic material from multiple parents, and a very small mutation rate is used, typically 2% or less, but never 0. Remember, if your mutation rate is 0, you don't have enough diversity. In fact, I've got a program that illustrates this quite nicely. I'll add a link in the video there at the top, so have a look there, click on that, and that will basically then show you what is the effect of different mutation rates. It's a simple program, but I think it illustrates the point quite nicely. Now, these values, PC and PM, are usually static, but they could also vary. So you can make them, they perhaps start with a high mutation rate and then decrease over time. You can, and in terms of defining them statically, that could either be empirically defined, so you have to thumb suck until you get a good approach, or using something like a grid search or something like that to find good values for your PM and PC. Now, when we talk about replacing individuals in your population, there's typically two schools or two ideas. You can have a generational genetic algorithm where the offspring replaces all the parents, regardless of how good the parents are. And then you also have a steady state genetic algorithms, or SSGA, or incremental GAs. Now, here the decision is made directly after the offspring is created, whether it's going to replace the parent or whether the parent is going to, keep on surviving and the offspring is not going to survive. And the amount of overlap between the current and the new population is referred to as the generational gap. So you could have a individual that's 4 or 5 generations old, and a younger solution that might only be 1 generation old or brand new in the actual population. Now, for SSGAs, we need to find a way on how are we going to replace an individual in the population with this newly created individual. So you could have a replace worst, take the absolute worst individual and replace that. You could have a replace random. So in other words, you could replace the best one in that if it's chosen by random. You could have a kill tournament, which is very nice. So here you select a random subset of the population and you replace the worst in that subset. This gives you a lot of flexibility, to tweak your exploration and exploitation as well. You could replace the oldest one, regardless of its fitness. Now, the idea here is if it's quite old, it had substantial amount of time to already contribute its genetic material. So you can just as well replace it to avoid it taking over the entire population. You could have a conservative selection. So here the oldest individual competes in a tournament with a random individual. So a random one plus the oldest one, and the weaker one gets replaced. And then you've got elitism or elitist. Now here the best candidate is excluded so that you cannot replace the best individual. So you're going to combine elitist perhaps with replace random. So the best one is not going to get replaced, and any one of the other ones could possibly then be replaced. And then, of course, parent offspring. And there's a number of combinations here. Typically, the offspring can replace one of its parents, or you could even have a scenario where an offspring replaces only one of the parents if the offspring is better than that parent, etc. But the idea is now only the parents and the offspring compete with one another in a kind of a tournament to decide who survives to the next generation. Now, standard GAs have typically a fixed size, and it may happen that a good individual is found, but then some genes is still unoptimal. And it might be very time consuming to find an absolute optimal solution because you only have crossover and mutation to change those specific parts in the individual's chromosome. Now, Goldberg developed what's known as the messy GA or MGA. And this algorithm evolves individual building blocks, and then it combines these building blocks to create complete individuals. So for example, let's say you've got a 4-dimensional problem, so nx equals 4. And let's say you've got a building block that consists of 2 genes at a time. So you could have 2 building blocks that form a complete individual. Okay, and basically what this indicates is in position 1 we have a 0, in position 3 we have a 1, and then the next building block specifies in building block, or in position 4 we've got a 0, and in position 1 we've got a 1. And immediately you're going to see that there's a problem here, and because an individual can be underspecified because there's a missing 2. Where's position 2 in this? There's no position 2. And it can also be overspecified. There's 2 position 1s. Now, typically this could be resolved either by a majority vote in case of overspecification, or in both cases you could use a competitive template to fill in those dubious uncertain areas in the actual chromosome. And in that way, you can represent your chromosome of your individual by these individual building blocks. And the idea is that you evolve these building blocks based on the fitness of the individual in order to find the best building blocks that you can use. So the standard SSGA algorithm uses an inner and an outer loop, where the inner loop consists of three main steps. The first is the initialization phase. Now here we create a population of building blocks, which is basically all possible combinations of building blocks. And of course, this is one of the drawbacks of SSGAs, because if your building blocks is large and you have a large number of it, and your dimensionality of your problem is large, you're going to require quite a bit of memory to store all these building blocks. But then the next phase is, after you've got your initialization, is a primordial phase, which aims to generate small promising building blocks using a selection operator. So the population is halved regularly, retaining the better half. So in this process, we eliminate the building blocks which does not seem to work well. And in the end of this process, you're going to end up with a much smaller pool of building blocks that you can then use. And then lastly, you've got this juxtaposition phase. And in here, this combines the building blocks through cut and splice operators to actually result in the final solutions, which consists of these optimal building blocks. Now, for genetic algorithms, the fitness function determines which individual survives, and of course which are used for reproduction. Now, sometimes the fitness function is really difficult to define and maybe even impractical. And in these cases, you can be lazy and use a human element for that purpose. So this is often used for evolving art, music, and animations. And there's an interesting project on the internet called Electric Sheep that you can check out. But essentially, they show animations as a screensaver. This is a rather old project, and you can vote either by pressing the up or down arrow to define to specify whether you like it or not. And all of this information on the internet is then gathered, and it's used to recombine the animations, and then the whole process repeats. So the actual humans on the internet is the fitness function, and this is known, of course, as interactive evolution. Now, genetic algorithms really lend themselves to parallel implementations because the individuals do not have to interact directly with one another. So the main categories of parallel implementations are as follows. You can have a single population GA, like we've had up till now, and then the evaluation of the fitness function is distributed over several processes. This is quite often the easiest and most simplest way to speed up this process, because the fitness function quite often is the most expensive part of the genetic algorithm. You also have a fine-grained GA where each individual is assigned to one processing thread, and then a small neighborhood is defined for each individual, with selection and reproduction restricted to that neighborhood. Then you also have a multi-population or islandic GAs, which is quite interesting. Now you have multiple populations that evolve concurrently, each on its own CPU, and individuals migrate from time to time between these populations. What makes this quite interesting is you can even have different fitness function on each of these islands, and each of them optimizing a different aspect of the problem that you're trying to solve. Of course, for islandic algorithms, you're going to need a good migration policy. So the following components need to be considered. First of all, a communications topology, which determines the migration paths between populations. In other words, are all the populations connected? Are some of them off limits to certain other ones? A migration rate, which determines the frequency of the migration. A selection mechanism, in other words, which individual am I going to copy over to another population? Am I going to leave it, a copy of it from where it comes from, and just copy it over, or am I truly moving it over? How is that going to work? And then, of course, a replacement strategy, because if you move an individual over, a solution over, you need to replace one of them. So either something like a replace worst or a kind of a kill tournament perhaps, but you're going to need some kind of replacement strategy. Now, both static and dynamic islandic GAs exist, which are based on the migration paths and the selection strategies. Initialization of the population should be considered carefully. In other words, are you going to randomly initialize every island, or are you going to initialize just in certain areas of the state space, just to try and cover them as uniformly as possible, and not to maybe I have 2 islands search for exactly the same part in the search space. And as I've just said, the fitness function could also be varied. So one island can search for a specific problem or focus on a specific subdomain of the problem, and the other one on a different one. And in that way, you can combine them and find a good solution to the problem that you are trying to solve. Guys, and that's chapter 9. That's genetic algorithms. So at this point, I would like to urge you to try and write your own GA, even if it's something as simple as evolving a line of text. It could be very beneficial and will really help you, understand what's going on. So try and see if you can implement that. And contact me if you struggle with that. Also remember to have a look at that picture perfect demonstration of what happens when the mutation rate changes in a genetic algorithm. I'm sure you'll find that useful. The link is in the description again. Other than that, keep well, and I'll see you in the next one.